Good morning, students. We'll start with the today's lecture. We have started with the fourth chapter, stability analysis. Right, there are several ways of finding the stability of a system. Some graphical techniques are there, mathematical techniques are there in order to find out the stability of a system. In this chapter, we will see one of the mathematical technique in order to find out the stability of the system. That we call it as Routh-stability criteria. That we'll be seeing. Right. Okay. Uh, Already we have seen the introduction and concepts of stability. Yesterday we have covered. Then next in today's lecture, we'll see the necessary conditions for stability and we'll solve few numericals based on that. And we'll see the Routh-stability criterion and we'll solve few numericals based on that. Right? Okay. Necessary conditions for stability. What is right? If I say that system is stable, it has to satisfy this necessary condition, right? Okay, but there is something called a sufficient condition also. Sufficient. There are two conditions: necessary condition and sufficient condition. But initially, we will see the necessary condition for stability, right? So, if I say that the system has to be stable, means it has to satisfy both necessary condition as well as sufficient condition. Both it has to satisfy, right? Okay, if necessary condition is satisfied, then I can say that system may be stable. I will not say that system is stable. I will say that system may be stable. Right? Okay. But if necessary condition is failed, then I will say that system is unstable. No need to prove for sufficient condition. Right? So, if I say that system is stable, means it has to satisfy both necessary condition as well as sufficient condition. Okay. First, we will see the necessary conditions for stability of a linear time invariant system, LTI system, having single input, single output system. SCSO means single input, single output. Okay, let us assume that the system is described by the characteristic equation Q of S, general equation. Q of S is equal to A naught into S power n plus A1 into S to the power of n minus 1 and so on plus An equal to 0. A naught is greater than 0. This is greater than 0. For example, let us take this equation S cube plus S square plus 2S plus 8 equal to 0. Right here, this is the third order. This is of the third order. Here, the general equation we have taken, it is nth order, right? Okay, observe what are the necessary conditions so that we will call that system is stable, right? Okay, all the coefficients must be real and should have the same sign. Either all should be positive or all should be negative. Here the coefficients are A0, A1, An minus 1 and An, right? Here all should be positive and they should have the same sign, means either plus or all should be minus, right? They should have the same sign. And none of the coefficients should be 0, right? Yes, observe here, if I take this for example this characteristic equation S cube plus S square plus 2S plus 8, observe here all the coefficients are present. Observe the coefficient of S cube, it is 1. Observe the coefficient of S square, it is 1. Observe the coefficient of S, it is 2. And constant term last, S to the power of 0 means it is 1, so it is constant term is 8. Observe all the powers of S are present. First S cube, then S square, then S to the power of 1, S to the power of 0. None of the terms are missing here, means all the coefficients are real and they are having the same sign here, plus plus plus, right? And they should not have one. Suppose this term is having plus, this term is having minus. No, that is not okay. All should be either plus or all the coefficients should be either negative, right? And none of the coefficients should be 0, means suppose if the S square is not, if S square is not there, suppose the equation is like this: S cube plus 2S plus 8. This S square is not there, means one of the coefficient of S square is 0, means the coefficient of S square is missing. So at that time necessary condition fails, right? Okay, observe that if it satisfies two conditions, then I will say that yes, it has satisfied the necessary condition, and I will say the system may be stable if it satisfies these two conditions. One condition is all the coefficients must be real and should have the same sign, either positive sign or negative sign, and none of the coefficients should be 0, right? Just by inspection of the characteristic equation, that is coefficients of the characteristic equation, we will get some conclusion regarding the stability of the system. If it satisfies these two necessary conditions, I will say that system may be stable. I will not say that it is stable. Please observe my wordings. It may be stable, but I will not say that it is stable. When I will say that it is stable, next I will go for proving the sufficient condition. Means how to prove the sufficient condition? There are two ways. One way is finding the roots of the characteristic equation and locating the poles where they are located. If they are located in the left half of the S plane, yes, system is stable. If they are located in the right half of the S plane, system is unstable. If they are located on the imaginary axis, system is marginally stable. These things we know. But that thing we will not do here. We will not find out the roots of the characteristic equation. Another method is we will make use of the Routh criterion, Routh stability criterion, in order to judge the stability of the system. That I will cover later, right? Okay, right now we'll take up one example. S cube plus S square plus 2S plus 8 equal to 0. The question is determine the system stability by inspection. Just by observing this equation, we have to find out by inspection and solving the roots of the given characteristic equation. Here we will solve the roots and find out what is its stability, right? By inspection and by solving for the roots. We'll see one by one. All right. Okay, observe here s cube, all the powers of s are present here. S cube is there, next s square, it is not missing, it is there, right? All the powers of s in the decreasing order. Highest power of s is 3, then s square, s to the power of 1, s to the power of 0 means is constant term, means all the coefficients are positive and none of the coefficients are 0, means the system, the given characteristic equation satisfies necessary condition. Necessary condition means these two conditions, right? Necessary condition. Hence given system may be stable. I am using the word maybe. I am not telling that it is, may be stable. Observe the word maybe, right? Then when to say that clearly that it is stable, then I should solve the roots. This is one way. Another way is by making use of Routh criteria. We have not yet studied what is Routh criteria. Right now we will solve the roots of the characteristic equation. So we will try to solve the roots, find roots of characteristic equation, find roots. Okay, we'll find the roots. So I will make use of calculator here. So I am using my calculator. I will go to equation in my calc, then I will go to degree. It is third order equation, so I will taken. Yes, it is asking for value of a. I will give 1. Coefficient of s cube is 1. Coefficient of s square is 1. I will give. Then coefficient of s is 2. The next constant term is 8. So I will write the roots what I am getting. So the roots are s is equal to minus 2 is one of the root. The next 0.5, 0.5 imaginary I am getting, let me check it, plus j of 1.936. This is another root. The next another root is once again plus 0.5, imaginary minus 1.936 minus j 1.936. So these are the three roots. Observe that the roots, but since the given characteristic equation the system satisfies necessary conditions, so given system may be stable. So just by we will observe the roots where they are located. You can observe here this one of the root minus 2 is located in the left half of the s plane. Observe these two roots 0.5 plus or minus j. Since these two roots are located in the right half of the s plane, so given system is unstable. Now I will say very much clear. I am not. I don't have any dilemma. Clearly, I will tell that the given system is unstable because try to locate the roots in the s plane. Whatever you got, right? So sigma j omega. This is the s plane. So one of the root is located at minus 2. This is the pole. Then 0.5 here. Sorry, 0.5 plus j 1.36 here, right? So yeah. Right, so j 1.936. Similarly here minus j 1.936. Okay, one of the root is lying in the left of the, but observe these two roots are lying in the right half of the s plane. Now I am very much sure that so given system is unstable because two roots are lying in the right half of the s plane. Because if I say that if the system has to be stable means all the roots should lie in the left of the s plane, but since these two roots are lying in the right half of the s plane, so given system is unstable. If one of the root is also lying in the right half of the s plane, then also I will say that system is unstable. Please try to understand, right? If any doubts, please unmute yourself and talk to me so that I can clarify your doubts immediately. Okay, next example we will take up s cube plus s square plus 10s plus 48 equal to 0. Okay, observe whether all the powers of s are present. Highest power of s is 3, then s square s it is present, s power 1, s power s it is satisfied and all the coefficients are positive. Suppose let me take another equation like this, the same equation s cube plus 10s plus 48. Just observe, yes, s square term is missing here. If I take this example, right, so s square term is missing, s square term is missing, and the coefficient of s square term is 0. So it is not satisfying necessary condition. Hence, I will say that given system is unstable. Clearly, I will say that given system is unstable, right? But let me take this example now. So, since it is satisfying necessary condition is satisfied. Necessary condition is satisfied. What I mean if I say necessary condition is satisfied means these two conditions. All the coefficients are real and have the same sign. Here they all are having positive sign and none of the coefficients are 0, right? So necessary condition is satisfied. Hence given system may be stable. I will not say it is stable, may be stable. Then we'll go for proving the sufficient condition by solving the roots of the characteristic equation, right? So we'll go for proving the sufficient condition. There are two ways of proving the sufficient condition. One is solving for the roots, another one is Routh-stability criterion. We have not yet studied, right? So find the roots of the given equation. Once again, I will make use of calculator. Okay. I'll go to mode, I'll go to equation, then I'll go to degree 3. Yes, it's asking for value of a, it is 1, s cube coefficient, s square coefficient is also 1, s coefficient is 10, then constant term is 48. So I'll write the roots what I am getting. So s is equal to minus 3 is one of the roots. Next second root 1, 1 plus j 3.872. This is another root. The next third root 1 minus j 3.872. Just by looking at the roots, can you tell one of the root is lying in the left half of the S-plane, but these two roots are lying in the right half of the S-plane. So given system is unstable. Right? Given system is, now I can very much clear that after proving the sufficient condition, clearly I will tell that given system is unstable. Try to look at the roots. So minus 3 is here. Minus 3, then plus 1 plus j something here, the roots are coming here, sigma j omega. So 1 plus, this is 1 plus j 3.872, 1 minus j 3.792. So since these two roots are lying in the right half of the S-plane, so given system is unstable. Right. I hope it is clear to you people. Next, we'll proceed with the next topic. Okay. Then I have the characteristic equation. Just I am using the short form CE. CE means characteristic equation like this, right? Okay, one or more coefficients of the characteristic equation can be 0 or negative. Only if there are three possible cases when the coefficients of the given characteristic equation can be 0 or they can be negative. Means s square term is missing means yes, one of the coefficient is 0. Or it can be negative means instead of plus it may be minus 10s, for example, right? So I will write two equations here. S cube plus 10s plus 48 equal to 0. This is one characteristic equation. Let me take another characteristic equation. S cube plus s square minus 10s plus 48. Observe here, in this s square term is missing and coefficient is 0, right? That is one thing. And another thing you can observe here, all the sign of the coefficient should be positive. Here it is positive, here it is positive, but here it is negative. It cannot be mixed. Either it should be all positive or all negative. So one of the coefficients is either 0 in this case and negative in this case. When it is possible, when there are three cases. First case is whenever the one or more roots are lying in the one or more positive real parts are lying in the right half of the S-plane. Positive real parts, right? One or more positive real parts or one or more roots are lying in the right half of the S-plane, right? Positive real parts here. For example, plus 2, plus 3, right? This is first case. At that time, I will come to know that if the roots are lying here, I will come to know that either the coefficient is 0 or negative. There may be two cases. The characteristic equation may be having the coefficient, one of the coefficient as 0 or the coefficient may be negative. This is one case. Second, this green color I have marked here. One or more roots on imaginary axis, complex conjugate roots, one or more complex conjugate roots or conjugate roots on the imaginary axis. For example, plus j2 minus j2. This is second set, plus j2 minus j2. And at that time I will come to know that either one of the coefficients of the given characteristic equation 0 or negative, right? In third case, if one or more roots are lying on the at the origin in the S plane, right? At S equal to 0, maybe one root may be present, or double roots or triple roots may be present here, right? So in all these three cases, when one or more repeated roots on the right of the S plane, that too on the real axis, at that time I'll say that the coefficient of the given characteristic equation may be 0 or negative. Another is complex conjugate roots on the imaginary axis, one or more complex conjugate roots on the imaginary axis. Here one set I have shown, there may be two sets or three sets. Then one or more roots at the origin of the S plane, right? Finally, conclusion what we will make, the coefficients can be 0 or negative, and stability is system is either unstable or limitedly stable, because if the roots are repeated on the imaginary axis, system is unstable. But if the non-repeated roots are present on the imaginary axis, system is limitedly stable or marginally stable. If the roots are located on the right of the S plane, system is unstable. So whenever the coefficients are 0 or negative, at that time system can be either unstable or limitedly stable. Please keep in the mind, right? Okay. The next, necessary conditions for stability. To analyze the stability, first what we should do, first the characteristic equation is examined for necessary condition, whether necessary condition is satisfied or not. If it is satisfied, I will say that system may be stable. If it is not satisfied, then system is surely unstable. No need to go for proving the sufficient condition, no need to solve the roots, right? So compulsory necessary condition has to be satisfied for the stable system. The next second one is, if one or more coefficients are 0 or negative. When the coefficients can be 0 or negative, it can be concluded that system is either unstable or marginally stable. Just now we have seen this, right? We have made the conclusion. The second point is same thing, right? If one or more coefficients are 0 or negative or for the given characteristic equation, then it can be concluded that system is either unstable or marginally stable, right? Then next, third point, if all the coefficients are positive or all negative, the possibility of stable system exists. Yes, this is satisfying the necessary condition, because all the coefficients are positive or all negative, so system may be stable. And but that is not the thing to tell that system is stable. System may be stable. Then I should go for proving the sufficient condition, either by making use of Routh criteria or for solving the roots of the character. This we have seen already. Solving for the roots of characteristic equation, we have seen in the two examples here, right? This one example and this one we have seen, right? The next, by using Routh criteria, how to do it, we'll see it later, right? Okay. So sufficient condition can be proved by either using the Routh criteria or by solving for the roots of the given characteristic equation. Okay, we'll take few examples here. Investigate means no need to solve, just inspection or investigate whether the following systems represented by the characteristic equations are stable or not. Okay, let me take first one. A, observe party, s power 5 plus 4s to the power of 4 plus s square plus s plus 2 equal to 0. Observe, just necessary condition is satisfied or not. Observe here. Yes, highest power of s is 5, s power 4, s cube is missing, so s cube term is missing, but s square, s power 1, means s cube term is missing, s cube term is missing. If s cube term is missing means, what is the meaning of that? Means the one of the coefficient, means coefficient of s cube term is 0. So s cube term is missing and its coefficient is 0. And its coefficient is 0. So if its coefficient is 0, what is the conclusion I will make? System is either unstable or marginally stable. System is either, that is one thing, right? S cube term is missing. But since necessary condition is failed, because s cube term is missing and its coefficient is 0, but will not make use of this condition. Means its coefficient is 0, either system can be unstable or marginally stable. Since necessary condition has failed, condition has failed, so given system is unstable. So given system is unstable. Very much clear, right? If necessary condition fails means given system is unstable. No need to go for further proving the sufficient condition either by solving for the roots or Routh criteria. But if it does find out, you have to find out, right? Then part B will take up second one. 5s to the power of 4 minus 2s cube plus 3s square plus 2s plus 16 equal to 0, right? Okay, observe all the powers of s are present. S power 4 has s cube, s square, s power 1. Yes, all the powers of s are present. But observe the sign here, plus minus means, so since the coefficient of s cube term is negative, right? Since coefficient of s cube term is negative, necessary condition fails. Necessary condition for stability fails. Necessary condition for stability fails. Necessary condition fails. So given system is unstable. This is very much clear. Just by inspection we are doing, just by inspection, right? We will observe whether all the coefficients are positive or negative, or any of the coefficients is missing or 0, right? Then part C. So 12s cube minus s, 12s cube minus s, 12s cube minus s plus 10. Okay, observe s cube, s square term is missing, s square term is missing, this is one thing. Then what is happening once again? This, the coefficient of s power 1. So coefficient of s power 1, right? This is s power 1. No need to write s, simply s. Coefficient of s is negative. The coefficient is of s is negative, right? So necessary condition fails. So necessary condition fails. Necessary condition fails. If it fails, means given system is unstable. Okay, D. S power 4 plus 2s cube, s power 4 plus 2s cube plus 5s square plus s. Can anyone tell whether given system is stable or unstable just by inspection? Last one here, s power 4 plus 2s cube plus 5s square plus s equal to 0. Can anyone tell whether necessary condition is satisfied? Please unmute yourself and tell. Given system is stable or unstable?
Unstable.
Unstable. Why it is unstable? Can you tell?
S raised to 0 powers.
S power 0 means that term means one of the coefficient, right? Constant term is missing, right? Constant term is missing. Yes, good. Observe, highest power of s is 4, s cube, s square, s power 1. S power 0 should have something. That term is missing, means constant term is missing. Constant term means s power, there should be plus 1, plus 2, something like that, right? So constant term is missing, means coefficient is 0. That particular constant term coefficient is 0. Constant term is missing. So necessary condition fails. The same thing, whatever I have written, this one. Necessary condition fails. So given system is unstable. Okay, one more thing. It is not asked. I will give you. You tell, all of you tell. S power 6 plus 10 s power 5 plus 6 s to the power of 4 plus 5 s cube plus s square plus s power 1 plus 2 equal to 0. Whether given system is stable or unstable, party, can anyone tell? Just by inspection?
Maybe stable.
Yes, may be stable. Yes, good. Because necessary condition is satisfied, may be stable. May be stable. Yes, good, very good. May be stable because necessary condition is satisfied here, right? May be stable. If I want to tell if it is stable or not clearly, then I should go for proving the sufficient condition. Good, very good. Next, I will take another numerical. Example 5.2. Without using the Routh criterion, determine if the following systems are asymptotically stable. See here, observe here. Instead of telling asymptotically stable, simply I will use the term stable, right? Asymptotically stable means already I have told. What is asymptotically stable system means? If I don't apply any input for the system, the output should tend towards zero. That I will call it as asymptotically stable system, right? Okay. Here we have to determine if the following systems are asymptotically stable, or marginally stable, or unstable. In each case, the closed loop transfer function is given. Yes, part A, let me take it. The closed loop transfer function is given. Let me take part A. M of S is equal to 10 into S plus 2 divided by S cube plus 3S square plus 5S. It is given. So this is the closed loop transfer function. Observe here, it is closed loop transfer function. Just observe the denominator polynomial. So I will take the characteristic equation, CE I will write. So characteristic equation means observe the denominator, right? That is characteristic equation. S cube plus 3S square plus 5S equal to 0. You can equate it to 0, characteristic equation, right? So observe the characteristic equation, all the powers of S, S cube, S square, S power. Since constant term is missing, so constant term is missing. Constant term is missing. So given system is unstable. Constant term is missing, so given system is unstable. Is it clear? Okay. Then next. But observe here what they are telling. Yes, fine. Without using determine if following systems are I have to tell clearly, right? And now it is very much clear that given system is unstable. Is it fine? But I will ask you people to find out the roots also, roots of the given characteristic equation. Let me find out the roots and we will prove that also. But no need to prove. Once constant term is missing means I will clearly tell that system is unstable. Is it fine? Okay. Okay. Just by inspection I came to know that system is unstable, but no need to go for proving the sufficient condition. But let me try to find out the roots by using calci. So I will go to equation, then I will go to degree 3, then coefficient of S cube is 1, coefficient of S square is 3, then coefficient of S is 5, then constant term is 0. So the roots, let me write the roots. 0 is one of the root, then minus 1.5 plus j 1.658. Then next another root minus 1.5, sorry, 1 minute, x2 x3. So plus or minus, so minus both two roots, totally 3 roots, right? So you can observe here one of the root is on the origin, right? So one of the root is on the origin, you can see here. So one of the root is on the origin. What about the remaining two roots, this sigma j omega, right? So minus 1.5 here, minus 1.5 plus j something, right here. Is it fine? I hope it is clear, right? But observe here, since these two roots are lying in the, but one of the root, if only one of the single root is at the origin, what is the meaning of this? What is the meaning here? See here, we will not worry about these roots because they are already lying in the left of the S plane. But one of the root is lying at the origin. If the single root is lying at the origin, what is the meaning? Then what about the stability of the system?
Stable or marginally stable?
Stable or marginally stable. But it is marginally stable. It is marginally stable because one of the root is non-repeated root is at the origin. So it is marginally stable. Marginally stable. Is it fine? Marginally stable. It is very much clear. It is marginally stable. Because, okay, now it is not asked here. What is the response I am getting if one of the root is lying at the origin? What is the response I am getting? Response is constant amplitude, right? I will be getting constant amplitude like this, right? Yes, the response will be constant amplitude, right? It is constant. I hope you know this. Already we have seen yesterday the location of the roots and its response. You should correlate all those things, right? Is it fine? Okay, fine. Then next we'll go for the second one, right? Yes, second one B, m of s is equal to s minus 1 divided by s plus 5 into s square plus 2, s square plus 2. Okay, without using Routh criteria means we don't know what is Routh criteria right now, so without using that we have to do means without using that means solve for roots, solving for the roots only, right? Okay, we'll go for the characteristic equation. So s plus 5 into s square plus 2 equal to 0. Yes, it is correct. So we'll find out the roots. So s equal to minus 5, sorry, minus 5 is one of the root. Then s square plus 2, s square equal to minus 2. So the roots are, yes, we'll find out the roots. So what is what I will be getting? Plus or minus j root 2, right? Yes or no? Plus or minus j root 2. Yes, is it correct? Just please tell me if it is wrong. Let me. S square plus 2 equal to 0. So coefficient is 1. So b s power 1 coefficient is not there. It is 0. Then constant term is 2. So it is plus j 1.412. Right? Plus or minus. It's correct. Plus or minus j 1.414. Root 2 is 1.414. It is correct, right? Okay, fine. Look at the roots. Sigma j omega. One of the root is located at minus 5, then plus j root 2 and minus j root 2, plus j root 2 and minus j root 2. Can you tell what is the stability of the system here? Anyone?
Unstable.
No.
Marginally stable.
Yes, it is marginally stable, because observe here, this one of the root is lying on left. We will not worry about this since non-repeated roots are on the imaginary axis. So given system is marginally stable. Marginally stable. Because non-repeated roots are there on the imaginary axis. This in the previous class we have discussed all these possibilities, right? Okay, we should be knowing that. Then I cannot go on doing all these things. Let me take up the last one. I will leave you do it. Just I will round out what you have to do. Part C you do it, part D you do it, part E I will take the s power 6 is there. I will take F, right? C D E is homework. This is homework. C, this is homework, and this is homework. But I have given the answers also. A is MS means marginally stable. Part B marginally stable. Part C, S means stable. Part C stable. Part D is also stable. Part E is unstable. Part F we will take up, right? So part F I will take. I have given the homework for you people. You do it. C D E. So F M of S is equal to 10 into S plus 12.5. 10 into S plus 12.5 divided by s to the power of 6, 4s power 4, 5s square plus 2. Yes, this is sixth order. I cannot solve in calci also, right? So yes, characteristic equation is s power 6 plus 4s to the power of 4 plus 5s square plus 2 equal to 0. Just by inspection, I will come to know that s power 5 term is missing. Its coefficient is 0. S cube term, its coefficient is 0. So given system is clearly unstable. It is not satisfying. But still, we have to find out the roots, right? Because without using Routh criteria, I have to tell me the another method is solving for the roots. If I don't use the Routh criteria, I have to solve for the roots. So how to solve for the roots? Let me put x is equal to s square and solve it. Put x is equal to s square. We call this as equation 1. In equation 1, put x equal to s square, right? So what I will be getting? X cube, right? So s square means s power 6 I am getting. So equation 1 implies equation 1 implies, so 4 x square means s power 4 I am getting back, 5x plus 2. This is one way of doing it, right? So I am putting x is equal to s square and solving. Now I can solve this cubic equation in the calculator. So I'll make use of calc for solving this. So I'll go to equation, then I'll go to degree. Degree is 3. Coefficient of x cube is 1. Coefficient of x square is 4. Coefficient of x is 5. Then constant term is 2. Observe x cube, x square, x power 1. Yes, it's correct. It is 0. Sorry, 2. D. So I write the roots here, what I am getting. So let me write it here. I'll make use of this part. So x is equal to, so minus 2 is one of the root. Then next another root. Minus 1 is another root. Then, okay. I'm not getting 3 roots. I should get 3 roots now. Minus 2. It's not showing. Means any root is repeated. In calc it has to show no.
Minus 1 will be repeated, sir.
Maybe repeated. Maybe I cannot say, but I should be very much sure no how it is. Right? In calc it has to show all the roots no. But it okay. There is another method. Let me try for that. Okay. Degree is 3. A is okay. X cube coefficient is 1. X square coefficient is 4. X cube coefficient is 5. And this is 2. X1 is minus 2. X2 is minus, means yes. Third root is it is not showing, means minus 1 only. Right? Because we will take the second root will continue. Right? But what is x? X is s square. Right? So s square. So s square equal to minus 2. S square equal to minus 1. S square equal to minus 1. Totally 6 roots should come. Right? So s 1 comma 2, this first set of roots, plus or minus j root 2. This is one set of root. I mean this one, that is third comma fourth root, plus or minus, yes, they are all same, right? I think, right? So plus or minus j, right? Plus or minus j. Fifth comma sixth root, it is plus or minus j once again. Okay, we'll try to locate the roots. Sigma j omega. Okay, plus or minus j root 2, plus j root 2 minus j root 2, j root 2 minus j root 2. Then next, let me change the ink color. Plus or minus j. J means plus 1, right? It will be coming here. Then once again, the roots are repeated, plus or minus j at the same location, means let me change the ink color here. So here only same thing. Can you tell the stability of the system? The system is stable or unstable or marginally stable here by looking at the location of the roots? Can anyone? And you have to justify your answer also. Please unmute yourself and talk to me. Plus j minus j. 6 roots, right?
Unstable.
Unstable. Why it is unstable? Yes, it is correct. It is
Roots are repeated.
yes, repeated roots are there on the imaginary axis. Since repeated roots, plus or minus j, plus or minus j. Since the repeated roots are there on the imaginary axis, so given system is unstable. Yes, good, very good. Okay, so you take the homework C, D, and E. Take the screenshot and take it as homework, right? Okay, still time is there. I will continue the next topic. And I have given the answers here. For part C it is stable, part D it is stable, part E unstable, right? You solve the roots and try to find it out. And there is another method also to find out the roots of this sixth order or cubic equation. But anyhow, we are making use of calculator, we will get it, no problem, right? Okay, I will not discuss that method. Okay, next we'll study the Routh-stability criteria. Okay, if I want to say the system is stable, means first thing is it has to satisfy necessary condition. Necessary condition. First, then second one, it has to satisfy sufficient condition. sufficient condition. What is necessary condition? It has 2 points. One is all the coefficients should be having the same sign, either positive or negative. And another one is none of the coefficients should be 0, right? So all the coefficients should have the same sign and none of the coefficients should be 0. Then only necessary condition is satisfied. If necessary condition is satisfied, I will say that system may be stable. I will not say that it is stable. May be stable. But in order to tell clearly that it is stable or unstable, then I have to go for prove the sufficient condition. Prove this sufficient condition. There are two things in sufficient condition. One, by solving the roots of the characteristic equation, solving the roots of the given characteristic equation of the given characteristic. This is one thing, and another one is by making use of Routh criterion, Routh-stability criterion. Routh-stability criterion. Now we are going to study this. Criteria or criterion, right? One and the same criteria, right? Okay, next. Already solving the roots we have seen. Next we will see the Routh-stability criteria. Yes. Okay, then this was developed by Mr. E.J. Routh. The person has developed E.J. Routh. His name is E.J. Routh. So he has developed this algebraic criteria or mathematical technique in order to tell whether the given system is stable or unstable or marginally stable. He has developed this, right? Okay. First, how to do it? Step by step. Formulate an array of table called Routh array or Routh table. First, we have to frame the Routh array. You will not understand right now because if I take the example and if I explain it, then only you will understand, right? Just I will read out. Just try to understand. Formulate a table or array. That is, we call it as Routh array or Routh table. First, we have to build Routh array or Routh table using coefficients of the characteristic equation. We have to make use of the coefficients of the given characteristic equation and we have to construct or formulate the Routh array or Routh table. How to construct, I will tell you. Then, yes, if Routh array is there, let me take it like this, right? So let me s power 4 plus 3 s square plus 2s plus 1 equal to 0. So s cube is missing, right? So let me add, okay, let me make this as s cube only. S cube plus 3s square plus 2s plus 1. S power 3 s square, s power 1, s, fine. Okay. So first I have to list out the highest power of s vertically like this. S cube. Vertically or list out like this. S cube, then s square, then s power 1, then s power 0. S power 0. This is s power 1. So first list out the coefficients of s starting from highest power of s to lowest power of s vertically like this. Then, right? So this I am telling you how to form the Routh array or Routh table. How to construct. So just list out like this. Then in first row, this is first row like this. S cube row is first row. So first fill the coefficients using odd term coefficients. This is the observe here. Which are odd terms I will tell you. This is first term, second, third, fourth. So odd terms means first term and third term. This is odd terms. Then even terms means, let me take another in color. Even terms means second term. This is second term and this is fourth term. I hope you are getting. And this is, let me change the ink color. This is first term, and this is third term. First term, second term, third term, fourth term. So first, in order for the first row, first fill the odd term coefficients. Odd term coefficient, the coefficient of first term is 1 here. Then come to the another odd term. It is third term. Its coefficient is 2. Then fifth term is not there, over. Then fill up the second row. Even term coefficients means second term and fourth term I have to make use. Second term its coefficient is 3. Fourth term its coefficient means s power 0. Its coefficient is 1. Okay. You came to know how to fill the first row and second row. This is first row. By making use of odd term coefficients. Odd term coefficients have to be filled up. Then in second row, even term coefficients have to be filled up. Then remaining, how to fill up, I will tell you. Remaining rows are completed by the numbers obtained by the indicated operations for the 8th order system. Here, next example, they are taking the 8th order system. How to fill up this, I will tell you there next, right? Okay, let me take here only and tell you. but that would be better. I will skip this right now because I'll take the general example and discuss there. I hope this table consisting of the coefficients of the given characteristic equation, we call it as Routh array or Routh table, right? Okay, we will take up the general characteristic equation instead of this is example. So we'll see the Routh-stability, and this is the general characteristic equation is given. Q of s, 8th order, s power 8 means 8th order characteristic equation. A naught into s power 8 plus a1 into s power 7. Observe here all the powers of s are present. S8, s7, s6, s power 5, s power 4, 3, 2, 1, 0. If any of the term is missing, suppose this s power 6 is not there. If it is not there, I have to write like this. Plus 0 into s power 6 I have to write if it is missing. If it is not there, if it is not given, I have to write 0 into s power 6 before constructing the table, right? Right, before constructing the table I have to add this term also if it is not given, but now it is given here, right? Will not worry. Okay, first list out the highest power of s power 8 vertically. See, I have, right, vertically like this. S power 8, s power 7, s power 6, 5, 4, 3, 2, s power 1, s power. Vertically we have listed. Then next, okay, is it fine? Then next, odd term coefficients means odd, just I will odd term. This one, this is odd term. Leave one term. This first term, third term, fifth term, sixth, seventh term, ninth term. Odd term. The coefficients are a0, a2, a4. So a0, a2, a4, then a6, a8, a6, a8. Odd term coefficients we have filled here. First row is over. Next, come to the second row, even term coefficients. Just I will. These are even term. Second term, fourth, sixth term, eighth term. Right? Coefficients. Write on the coefficients in the second row. That is a1, a3, a5, a7. a1, a3, a5, a7. Second row you have filled. Right? Then how to calculate? Next, how to fill this remaining rows? S power 6 to s power 0. Remaining rows. Observe here. Yes, yes, I want to fill up this element. Okay, right now this element is blank. Don't worry, nothing is there here. Let me call it as b1. How it will come? How to calculate this? Observe here. So just above this I have two elements, a0 and a1. So next, observe this above this and next row. So observe, we make use of the elements here. I will change the ink color. So how to get this? a1 into a2. So I will multiply like this. a1 into a2 minus a3 into a0, like this. So I'll start from here. First I should start from here. a1 into a2 minus a3 into a0 divided by this a1. So we will get this element. Let me call it as b1. Right? I hope you are getting. If any doubt, please unmute yourself and talk to me so that I can clarify your doubts. So this element is b1. How to calculate this element b1? a1 into a2 minus a3 into a0 divided by a1. So we got this. This is how it is filled, right? Calculate it. Whatever the value you get, you write it here. But this is general characteristic equation. So we will keep in terms of a1, a2 only. Next, how to calculate this second element? Let me call this as b2. How we will calculate? How we will come to know this? Okay, just okay, we'll change the ink color. I'll take blue. Just observe, I want to calculate this element here. What is this? So you not just leave this row above it. Don't take a2, a3. Just above it you leave it. But this column is fixed. a1, a0 and a1, they are not going to change. We have to take these elements. Whether I calculate this the third row element, either first element or second element or third element or fourth element in the third row, this a0, a1 is fixed. Then leave this row just above this. I am leaving this. Then go to the next column. Use this row and this row to calculate. So a1 into, just observe here, a1 into a4 minus a5 into a0 divided by a1. So a1 into a4 minus a0 into a5 divided by a1. So we will get b2 element. I hope it is clear. Then how to calculate this b3 element? b3. So they have written the same procedure. Leave this row. Let me change the ink color. Let me use some green color here. Right. So how to get this b3 element? So observe here, leave this column, leave this. First column is fixed and use this column. This and this. Right? First column and this column. Leave this column. You should not use this. So a1 into a6 minus a7 into A naught divided by A1. So the A1 into A6 minus A naught into A7 divided by A1. So we got this. Similarly, we calculate this, right? Okay, observe, leave this. But this row means nothing is there means you have to append 0. You can write 0 here, right? So A1 into A8 minus A0 into 0, A0 into 0 divided by A1. So you will get this element B1, B2, B3, right? But no need to calculate this last element. You will get A8 only, always. That we will see it later, right? This is an S shape like this. Just let me observe here. Observe here. It will start here like this. Then I am getting A8 only here. Then next it continues like this. I am getting A8. It will be A8 only, right? This continues everywhere. Leave one column. Less I should leave. Here it is coming. I should leave one row. I should leave one row. A8 is coming. A8 is coming. A8 is coming. Just I am rounding. Just go like this. Leave this row. Here I am getting A8. Right? So no need to calculate these last elements like this. It is leave this row, leave one row, and we are getting A8. So no need to calculate these elements. Right? A8, A8 diagonally you can get. See? Right? Inverted L shape. You start here, go to this previous element, leave this one row and take this. Leave this row and take next row. Go here, leave this row, take next. Go here, leave this row next. Right? I hope you are getting how to calculate these last elements. Similarly, you calculate and fill up all the elements. This we call it as Routh array or Routh table. After getting Routh array or Routh table, what to do? Once we have the Routh array or Routh table, what to do? Just I have to tell whether the given system is stable or not. This Routh array or Routh table is very useful. It gives very useful information that how many roots are lying in the right half of the S-plane. How it will tell? That we'll see next, right? So Routh-stability criteria. Yes, no, we will note few things here. Missing terms are taken as 0. I told, suppose a2 into s power 6 is not given means you have to write 0 into s power 6 before forming the Routh array or Routh table, right? If it is here, it is given, no problem. Then once Routh array is formed, apply Routh criterion. How to apply Routh criterion we will see next. Already Routh array, how to construct Routh array or Routh table, it is very clear to you people, right? Yes, it is. I hope it is clear how to form the Routh array or Routh table, this table, right? Then apply the Routh criteria means that is to investigate the signs of the elements in the first column of the Routh array. Means we have to observe the first column elements of the Routh array. Means only this first column. This is first column. Just I am rounding it. This is the first column of the Routh array, right? This is the first column. Okay. After observing the first column, we have to observe for the sign changes, investigate the signs of the elements of the first column of the Routh array. Then what is Routh-stability criteria? What it states? Just I will read out. Observe here. For a system to be stable, it is necessary and sufficient that each term of the first column of the Routh array of its characteristic equation must be positive. If this condition is not met, means if all the elements in the first column of the Routh array are not positive, the system is unstable. That is very much clear. And the number of sign changes of the terms of the first column of the Routh array corresponds to the number of roots of the characteristic equation in the right half of the S-plane. Okay, let me take, okay, this is the Routh array or Routh table. Routh array or Routh table. General I will take. Okay, just I will observe the first column elements. Let me take s power 4, s cube, s square, s power 1, s power 0. Just I will fill up only the first column elements. I will not worry about the other column. Let's suppose this is 1, 5, 3, 2, 1, something like this. Observe the first column elements of the Routh array. Here all are positive. If all are positive means yes, system is stable. But if system is means suppose this is minus 5 for example. So one of the elements in the first column of the Routh array is negative here. Here we have to observe the sign changes, the number of sign changes. If any of the elements are negative here, then system is unstable. It is very much clear the system is unstable. Read this sentence once again after going through this example, whatever I am giving you. Read it once again, you will understand, right? So if all the elements in the first column of the Routh array are positive, then system is stable. But if any of the elements is having this is minus 5, for example, then since this element is negative, so given system is unstable. But this Routh array or Routh table gives very useful information that how many roots are lying in the right half of the S-plane. Because if I come to know how many roots are lying in the right half of the S-plane, This is sigma j omega. Then I will come to know that system is unstable, but I will come to know how many roots are lying in the, but I will not come to know the exact roots, but I will come to know how many roots are lying in the right half of the S plane. But that is number of sign changes. You can observe here. Let me change the ink color. Plus 2 minus, because plus 1 to minus 5, one sign change. So one sign change is there. First sign change, one sign change. Then minus 2 plus, second sign change. Then from 3 to 2, no sign change. 2 to 1, no sign change. Means 2 sign changes are there. Number of sign changes. How many times the sign changes? The number of sign changes. Here, how many number of sign? Number of sign changes here it is 2. Means this will tell 2 roots are lying in the right half of the S plane. Means in the right half of S plane, 2 roots are lying. So 2 roots are lying in the right half of the S plane. 2 roots are lying in the right half of the S plane. The number of sign changes will give me the number of roots lying in the right half of the S plane, but I will not come to know the exact roots. If I want to calculate the exact roots, means I have to solve the roots of the characteristic equation. I'll stop here. If any doubts, you can ask. I'll stop.